Okay, so the next thing we need to talk about is something called beats. And again, if you're a musician, you probably know what beats are. If you've ever tuned one instrument with another one, as they get closer and closer to being in tune with each other, you will hear beats. Beats are produced as a result of interference, and for us humans, we can only detect beats if the two objects, the two sources that are providing the sound, are within 7 hertz of each other. If they're more than 7 hertz, we'll hear them as two separate sounds. But if they're within 7 hertz of each other, we'll hear what's called beats. And really what's happening is it's constructive and destructive interference that's producing louder sound and quieter sound at different spots. Probably the best way for me to show you is to show you the diagram in the textbook, because it's better than what I could draw. Okay, so I'm looking at page 429. So at the bottom, so there's a green wave that has a frequency of 10 hertz, and there's a blue wave that has a frequency of 12 hertz. So they're within the 7 hertz of each other. Like I said, they had to be to create beats. When they start out, one is at a crest and the other is at a trough, so they're out of phase. And if you were to add them up, you would get 0, right? Positive, negative give you 0. But as they move along, because they're different frequencies, they eventually become in phase. So at this point, between the green one's second crest and third crest, it is at its trough, it is now in phase with the blue one. And so you get a big, huge resultant trough here. But then as it goes along again, because they're not quite the same frequency, they go out of phase again. So here at crest number 5 in the green one, they are now out of phase and you get very little sound again. Time goes on, they go back in phase again and you get a large crest trough and then out of phase. And so these are what beats look like. Low sound, loud sound, low sound, loud sound. The number of beats you hear as a result of the interference between the two waves is just equal to the difference between the two frequencies. So because one of these is 12 hertz and one of these is 10 hertz, the beat frequency would be 2 hertz, which means 2 beats per second. 1, 2. So we can hear up to 7 beats because we can hear beats whenever there is a difference of up to 7 hertz between the two objects. Okay, so there are 2 equations for beats. One is the beat frequency is just equal to one of the source's frequencies minus the other. And then we put these straight lines here. They mean absolute value. It's the difference between the two frequencies. Doesn't matter which one's bigger or which one's smaller. It can never be negative. So if you do 10 minus 12 and get negative 2, drop the 2. 12 minus 10, you get 2, keep, okay? Or drop the negative, don't drop the 2. Okay, so it'll be 2 hertz. The square brackets mean absolute value. Don't worry about the negative. But what if you had a frequency, something, your guitar string maybe, you're playing a frequency of, I don't know, let's say 450 hertz, and someone else is tuning their guitar with yours, and the beat frequency is 4 hertz. So what must be the other person's guitar? Well, there are 2 possible answers. It could be 454, could be 4 above what yours is, or it could be 446. It could be below what yours is. So the second equation for with beats is that the second frequency is equal to the first one plus and minus the beats. Okay? So you'll narrow it down to 2 possible things. Then you might have to do something to figure out which one it is. So if it was a guitar string, so let's say now the person tightens it and now plays it with yours, and now you hear 2 beats. once the person tightens the guitar string. So remember, when you tighten a string, you increase the frequency. So if the guitar string was really 454, it might go up to 455, 456, 457. And now when I play it with the 450, I should hear more beats. But I didn't. I only heard 2. So that means it must have been the 446, because when I tighten the 446, it goes up to 447 or 448 or 449. It's getting closer to the 450, and that's what the second round of beats tells us. So it must be the 446 originally. Okay, so that's beats. There will be a few for you to try tonight. It's kind of logic once you get to narrow this down, so it'll be good practice for you. One of the questions on page 431 has a mistake. It says one frequency is like 400 and something, and the other one is 300. They're not 2 apart. They're 102 or something like that apart. So just know that there's a typo in one of those. They both should be 400 and something. Okay? So that's beats. Next is forced vibrations. Forced vibrations. And there's a name for forced vibrations. It's called resonance. This is one of the coolest things in the world. Okay? One object can force another object to vibrate. Actually, my vocal cords are forcing the air molecules right above them to vibrate right now. When you beat on a drum, you're forcing the drum head to vibrate. But one object can force another object to vibrate without touching it if the other object has an affinity to vibrate at that particular frequency. So every object has what's called a natural frequency of vibration, all the way down to molecules. Remember that even in a solid, the molecules are vibrating. So every object has a natural frequency of vibration, a frequency at which it wants to vibrate. And if you feed energy in at that frequency, you can cause that object to vibrate. If you've ever seen or heard of an opera singer cracking a glass, it is exactly this principle that they're using. Okay, so they're singing, there's sound waves, and they usually pick like a pure crystal, something that has really only one element in it, so it would have all of the molecules would have the same frequency of vibration. So if that person can hit that particular frequency, that particular note, and hold it, they can keep feeding energy into this glass, and they will make the little molecules in the glass vibrate back and forth, back and forth, back and forth, and they'll keep getting bigger and bigger amplitude until they crack the glass. Okay? So if you can feed energy in at an object's natural frequency of vibration, then the object will start to vibrate. And not only will it start to vibrate, you will see, it won't just go like this, you will see huge spikes in the amplitude. Okay? There will be a dramatic increase in the amplitude, which will cause the glass to crack and a lot of other cool things to happen. Okay? So this is the principle of resonance. Probably one of the first places it was seen was in an army marching across a bridge in 1831. Armies usually march in step. Well, they don't march in step anymore across a bridge, because as this army was marching in step across a bridge going right, left, they were feeding energy in at a particular frequency, all in step with each other, and it caused the bridge to begin to oscillate as well, and the bridge collapsed. If you've ever pushed a child on a swing, you know that there's a certain frequency that you can push this kid at where you won't have to work too hard. But if you push at the wrong frequency, you have to keep pushing. But if you find the natural frequency of vibration, you won't have to push very hard. I don't know if you've seen the Tacoma. Oh, we're going to be out of time.